Other things like, PostGIS's wonderful functionality in terms of functions for calculating area of a multi-polygon. Those sorts of things, again, are derived data. And those are things we use all the time and we take for granted, right? The cool thing about Postgres is we can add more to that, right? So the next point I want to make clear here is what immutable means and what we need to use it to mean when we write our user-defined functions. There's a term in computer science called referential transparency, okay? Referential transparency means, very simply, that if I already know what the return value of a function is going to be, that I can just substitute that return value for the function call and everything continues to work, right? That means that the function is referentially transparent. It also means it's a function as we defined it before, not a procedure, right? Not a routine. Now, this means two things. For any given set of inputs, you can only have one output, ever. Like the same two inputs always lead to the same output, right? And the second thing is you can't have any side effects, right? If your side effects include, say, writing something else to another table, if you substitute the output for the function call, then that side effect won't happen, right? So if you need something else to happen, you don't have referential transparency. It's not a function in these terms. Now, how many people here know the term functional programming? A few. So functional programming is all about modeling your software using these sorts of pure functions to the extent you can, and therefore reducing the pieces of your software that actually have to interact with the outside world, right? And in databases, that's actually a really useful way to think about your problems. So enough about like the mathematical basis here. Now I want to talk about how B-tree indexes work, because along with that side, understanding the data structures and how an index actually works is really important for understanding what you can actually do with the index and what you can safely mathematically assume with the index. Now, this is a very simplified B-tree. Of course, most B-trees would be multiple levels like this. But basically, a B-tree is going to have bounding lists, and it will have pointers to the nodes that are going to handle that section. And then basically you can go down hierarchically, traversing that B-tree as a search tree to find eventually the leaf node that's relating to what you want, right? And in Postgres, that leaf node for at least our standard data table types is going to be basically a reference to the physical location on the disk where that record's found. It's a little, or at least the physical location within the file is a better, probably more accurate way to put it. So what this means is B-trees can then be used for a couple of very specific things, right? We can actually use them to identify specific rows based on values. We can identify rows based on ranges of values. But the really important one in this case is we could use them for ordering if we're only retrieving a certain number of rows. And Postgres can do all of this out of the box because these are safe assumptions for this particular type of index. So on top of this, what we're going to be talking about here mostly are expressional and functional indexes. So being able to index things that you haven't even stored in your database, which is actually can give you some really, really cool functionality. The last one will be a little bit about partial indexes. So indexing only some rows in the table. But there are many, many other things, right? B-trees are just one type of index that Postgres supports. You have gist and gin, and those give different kinds of capabilities. And then you also have a pluggable index access method that gives you things like rum, or I think for a while there was one called vodka, but it's no longer supported, which was specifically for certain geospatial stuff. And I think Oleg mentioned one for indexing the sky yesterday in his keynote also. So external or advanced index types are one major point. As I mentioned before, for B trees, you can use them for ordering and limit. And that's going to be very, very important as we get into these case studies. So, sorry about the typo on this. This is the first case study. This case study came from my work as a consultant working on a project at a major biotech firm in Denmark. Okay, and basically this was a big commercial enzyme manufacturing facility. So what they do is they identify proteins that do interesting things, they manufacture them, and basically then those go out in products. So when you buy laundry detergent, those might have enzymes to replace some of the detergents, and that's easier on the environment and stuff like that. So in order to support this, they had this big system that would allow researchers to basically search for enzymes matching specific criteria that they might want to do physical research in. Okay? Now, this system would have at its core one large table. That table, when I started, was about 3 terabytes in size, and when I left was about 6 terabytes in size. That table was called documents. Okay? And in that table, the main field was a text field called document. Okay? And the text field was machine readable. But it could be any of a number of formats. So you could have EMBL files which would describe the gene mapping location of a protein. You could have files that would describe the chemical properties of a protein. You could have files that would describe patents. Okay, and finally somebody says, hey, if I want to look at this protein, I need to see the last 10 patents that have been approved for the protein, because that'll give us an idea of whether we're going to run into patent problems if we research it. Okay, great. Where's the patent date stored? It's stored in that document. Great. Now you're dealing with a 3 terabyte table, and you want to order the last 10 patents for a given protein. First thing somebody tried to do, I kid you not, was select 10 patents and order them in the front end. Obviously, this doesn't work. It can't work. So the next thing we looked at was, do we want to add another field to this table and pull all the data? And the problem with doing that is less than 10% of these documents are patents. And so you're adding a field that's like null 90% of the time. Yeah, you can do it, but if you're going to do that every time you need something, things are going to get really slow. Or no, it's not really slow. It's going to get hard to manage over time, right? So the question is there a more elegant way to do this? There is. So, what did we do? We wrote a function that would take a row in for the document type, and it would return either a null or a date. Okay? Marked immutable, and we index the output. Okay? We index the output along with the protein ID, and now we can, for a specific protein, we can grab the last 10 patents. Using the index, we don't actually have to search through the table. Now keep in mind that there's one more issue here that we haven't talked a lot about performance-wise, and that's Toast. How many people here have experience with Toast and Postgres? A How many people know what toast is? Okay, so I'm going to explain this. So a Postgres data page is 8 kilobytes. Okay? What's the maximum size you can store in say, a text field in Postgres? 1 gigabyte. So how do you store 1 gigabyte of text in 8 kilobytes of space? You don't, right? What we do instead is we will compress it and then we will break it up into chunks and we will store those in another table called a toast table. Toast stands for the oversized attribute storage technique. And so then these are then queried whenever the data is actually used. And that data is then pulled out only when it's needed, right? So one of the problems if you actually try to query this data in the table itself, in the document itself, is that to extract this piece of information, you've actually got to pull the toast out, calculate it, and then discard it if you don't need it, right? So doing this on input when you index it actually is a big performance win for this reason. Fun fact, if you ever do an explain, analyze, select star from such and such, and it runs much faster than a standard select star, chances are it's probably toast because you're never using that data, and so explain, select star will never touch toast. Counterintuitive, but I guarantee you this is how it works. I've had multiple experiences on that side. So then all we had to do was we had to integrate it with the ORM. Everybody's going to think that's really, really annoying. The fun fact is Postgres allows you to, if your only input is a table type, so a row of a table, you can actually call it with the table alias dot in the function name. So in this case, you can kind of tell the ORM, hey, we have a fake field here. And usually the ORM will generate actually reasonable SQL. So yeah. So here's an example. I didn't include the actual code for the pulling out of the date. That's largely because space concerns on the side and the fact that handling Perl and LaTeX is an absolute pain. But basically what you can see here is we create the function, patent date, and it takes in the row type, right? So if the table is called document, we pass in a document type, and that's going to be a row. And then we create an index on basically these two fields. The first one being the patent ID, and the second being this expression of patent date of the document. And then we add a where condition, and now we have a partial index. That partial index only covers patents, and it's a relatively small index. And it's updated whenever we update the data. So now everything works. Before I go further, do people have any questions on this particular case study?
Yeah, I'm curious, how long did that take to create the index itself?
So, because remember, you only have maybe 300 gigabytes or less of actual patents in the table. I think it took like an hour or two.
But it didn't have to scan on the entire data set, right? To be able to identify the upload the function.
I think it, well, okay, yes and no. So the dot type is not a toasted field. So it wouldn't have to retrieve it only had to retrieve the toast for those, right? And this was a fairly big, beefy server. It had 3 terabytes of RAM, and the table was on pretty good, fast solid state storage. So it didn't take that long. It was surprisingly quick.
So,
one thing I did learn in that was create index concurrently almost never does what you want it to do. And the problem with create index concurrently is it sits there waiting for the snapshots to update. And if you run a big heavy system, that may take a lot more time than you expect. And if for any reason you cancel, you're going to have cleanup you have to do in startup. So, so when you create an index concurrently, what happens is it starts creating the index and starts updating it. But then it also notes the index as it will only be available after a certain transaction ID boundary has happened once it's gone through processing the entire table. Then it sits there waiting until all backends have progressed past that point. Okay?
So in a real-time production environment, if I have to create index in advanced direction just like this.
Then the problem you'll run into if you're using create index concurrently will have to do with if you have any long-running transactions, you'll have to wait for them all to complete. If you don't have any long-running transactions, you can probably get away with it.
So can it be solved by partial index?
So concurrently isn't going to solve that problem. If you have a partial remember, if you have a partial index, you're going. If you're creating index, it's going to block writes to that table while you're working. In this particular case, we could afford to block writes to this table for, as I say, like an hour or two while this was working. But in many other cases, you might have to sit down and think carefully about the way forward. And by the way, I think create index concurrently is something we could probably make a lot easier to work with.
And can I merge indexes?
Merge indexes. You mean like you have two single column
In
indexes?
this example, let's say I created a filter for doc type patent and there's another doc type. So I choose different time slots
Yeah.
to create one index for patent and one index for something else. And eventually I created a merge index of both of these so that I get benefit of it.
What you can do, well, in that case, you'd either have to do two queries with a union, or you could simply do a like a 3-column index, where you're also filtering on values on that first column. So there are ways of doing it, but you have to build it into the index. You can't merge them after the fact.
So I'm just trying to create a balance of
Yeah.
products and downtime and
Yeah, and creating products or balances of products and downtime, that's a pretty good description of a modern DBA. So, anything else before we continue on to the second one? All right, just a few notes. The downsides of this approach is that, like the whole ORM stuff, as I say, you can integrate it, but then now you have all this embedded knowledge of how does this integration work and that sort of thing. Also, there's a bit of complexity here, and well, you can verify values for given rows. Validating them over the entire index is something of a pain because you have basically this hidden layer here. Again, in this case, it was very much a trade-off that was worth it, but in other cases, you might want to actually pull it out into another column. The second thing, which happened in the same database, so we can just skip the background. So somebody comes back and they basically say, okay, so now we have this issue. We want to make sure that if somebody's actually doing research and trying to get this particular protein into production, we want to restrict who can see it. Because we don't want somebody to see what we're doing and then go find out more about this protein and then maybe sell it to our competitor, right? So the idea was then we were going to add access control lists to proteins and genomes. Okay, great, easy enough. But now we have to apply those access control lists to everything else in the database. That's the problem. Basically, you have a genome on one side, protein on the other side, and you have several joins necessary to get all the way across. And on every access, you have to check both ends. Anybody want to guess how well did this perform when they initially added it? I would just simply say it wasn't in the vicinity of usability for the researchers. I mean, it was more along the lines of, okay, we started search, now we're going to go get coffee and we'll come back later. One of the things we could have possibly done is try to duplicate all of this information across the whole join directions. The problem is you have questions of how well you can actually guarantee that everything's current. And the second problem that you have is that a protein could be attached to multiple genomes, and a genome could be attached, will of course have many, many, many proteins. So at that point, you're talking about massive duplication of information, and it's going to be extremely difficult to maintain, and extremely poor performing to maintain. So we decided that just simply wasn't an option, and the second option was live with bad performance. I mean, we ended up living with bad performance, but we wanted to live with usable performance. So how did we solve this? Now, the solution was to basically sit down and think about how does the database work. And the fact that you're just traversing these joins, you're not actually using any other data in there other than the join keys to get from one join to the next, right? And believe it or not, we actually do this a lot, oftentimes in our applications anyway. And so understanding this is something that may actually improve a lot of performance in many cases. So what we ended up doing was we ended up saying, if we can eliminate actual table access for all these things, then we can get the I/O down to a point where we hope the database will be usable again for people. By the way, this was all done with Postgres 9.3, I think. So we didn't have row-level security, so this was all done with views and triggers and stuff. I see other people going. Yes, it was a headache. And so what we did was we basically looked at the plans and we looked at how the joins would have to be traversed. We discovered that the ordering of the joins was actually fairly constrained in this particular case. So what did we do? We created multi-column indexes in the direction of the join orders, so that basically when we had one key, we could just look up the next keys, and then we could just basically go on to the next keys. And because in most cases you don't have a massive number of these sorts of checks, then it actually cut down on the I/O way better than I expected. I expected something like a 50%, cutting the query time in half. It actually did much better than that. Also keep in mind, system had a large amount of memory, so then these indexes ended up sitting in memory the whole time. So access was really, really, really fast. So this actually got everything back. It was still, I thought, slow, but it was suddenly usable again. And that allowed us to deliver a feature that was very much needed by the business, and that we would not have been able to deliver it another way. So, downsides. The biggest downside here is that now you're putting the query planner in a bit of a straitjacket, because one join direction is going to have a much, much lower cost than another join direction. So you could create multiple indexes to solve this, but then you're going to have all of the problems associated with more indexes, including more I/O when you do writes and all the rest of this, right? So the other side to this is that if you're constraining the planner in this way, you need to be pretty aware of it, and you need to be thinking about the fact that this is going to make certain troubleshooting perhaps a little more difficult. So those were probably the two biggest ones. seeing if I missed anything. No, I didn't. This is the area where it's in fact quite useful, but it adds quite a lot to the reasoning burden. On this case study, are there any specific questions?
Yes, right. Understand it correctly. You still have all the tables what you had, right?
Yeah.
You solved it with the index-only scans by indexing or treating multi-column indexes, right?
Yeah.
Can you give me an example? Because that is something we deal with and would be helpful if I can apply.
Sure.
Yes, we did.
I don't have a complete example. I would say typically.
If you go back to the table
Yeah.
that you had, yeah.
So typically, if you're querying, for example, document, which is sort of the most common case, then to get to protein, you're going to have to go with protein ID document ID / protein ID, right? But to go over this way, you're going to have to go document ID, gene ID, and then here you're going to have to go gene ID, assembly ID, and here you're going to have to go basically assembly ID, genome ID. And then you will actually have to read the whole the genome entry because that's where the access control is. Okay. Though we probably could have put that in another index if we wanted to. I can probably spare just a couple minutes to explain what each of these tables are, but I don't know if that's of interest to people.
The actual index,
Yeah. Yeah.
I mean, just what are the columns that you used for the index-only scan? Because you.
So it's just foreign key and a primary key, but you have to think about which direction you're almost certainly having to scan.
So, you're saying like there is a direction of the index. So if I have to query on the reverse side, the index is not being used in that case.
The index will not be used, and that index will not be used. That index will hopefully not be used in that case. It might still try to use the index and filter, and you don't want that. So in cases where you actually have to start querying the protein table, then you might end up having to create both directions of indexes in that specific case.
And creating two indexes depending on the direction?
Yeah, I mean you can do that, but then you have all the extra writes and all the, and it may start pushing one out of the cache if memory is an issue.
So more and more index we create with the devices, we slow down the write operation. So how are we trying to?
Yes, the more indexes you create, especially the more columns you index, but even just the more indexes you create, it will slow down the write process. You have extra write-ahead log that has to be created. You have extra files that have to be updated, and if you're adding more columns to your indexes, which isn't the case in this particular issue, then you'll restrict more the cases where a heap only tuple updates can happen.
So can the index update in a lazy manner, like first?
So Brin updates sometimes happen this way. Gin indexes have some two-stage process. I'm not intimately familiar with how that works. But B trees, there's no real way to do an incremental, a lazy update of the B tree. All right, so on to the next one. And this is the one that was a pure partial index. This was a different place I worked, which was an ad tech company. And what we were doing is we were doing a lot of, trying to do real-time application stuff, basically real-time analytics for streams of data from people's interactions with applications that they pay for advertising on their phones, right? So data comes into the servers, let's say 200, but well, when I started it was maybe 200,000 requests a second. These then get processed and eventually sent on to customer-facing data warehouse. Okay, and we want to provide data to the application developers, typically real time to within half an hour. Okay, fun challenge. So the way that we actually did things was basically something kind of like a MapReduce. So data comes in, it gets stored in basically the servers, which are the point of entry servers, and then we basically we aggregate and send deltas over to the data warehouse environment. So the delta processing part here then becomes interesting because the point of entry servers would typically have databases of roughly 10 terabytes. And these are typically limited in size by the hard disk, right? We have recent stuff on SSD, we have old stuff on spinning disk, and we're only going to store basically about as much as we can store on the hard disk, and after that we're going to purge the data. How do we send these data? How do we send these deltas over? Well, fine, we just need to identify the delta, we aggregate it, we'll split it up to the nodes it goes to, and we'll send it over. But we can simplify that in our minds by saying we just aggregate the data and send it over to the environment, right? We can leave out of our minds the whole sharding question. So we want to also preserve as much of the data for as long as we can, because if something needs to be updated, let's say 2-3 months back, we can still update it and send the delta over, right? So we didn't really want to update, we didn't want to index all of the data on the system to identify the deltas. So what we did instead was we created basically the field, the tables all had a field. The field was materialized, we called it materialized. That just meant we had aggregated, we'd set the data over to send it over. And then we had a trigger that if you updated a row, would set that flag back to false and would archive the old version of the row so we could take it up. And basically from there, then we would create an index on the IDs of those fields only where materialized is false. So this means a very, 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 very small number of rows are going to be indexed at any given point in time, and this index will stay relatively small. Now, what this then means is that when vacuum runs, it will basically keep pruning that index down and keeping it small, and therefore we have lots of space for actually storing data. Of the 3 cases, this was the easiest. It was the one that added the least complexity, and it was the one that, on the whole, worked the best. The only thing you have to keep in mind is that there is a special index here for these very specific cases, and that index is probably not going to help you if you're doing anything else, and so you have to accept that it's a very specific query-oriented index, and it's basically for these very specific indexes. So I'll do the conclusion, and I'll come back for a couple more questions. Advanced index techniques are something that are really great to have in your toolkit. They allow you to get certain things done that would be extremely difficult to do in other cases. But they have a lot of complexity, and with that complexity comes a need to know more about what's going on, and especially when things aren't going well, that complexity can be a little bit of a difficult thing to deal with. So my recommendation always is have all these techniques in your back pocket, but don't use them unless the standard techniques are not really usable at that point. Again, as my college calculus teacher used to say, in mathematics, it's considered inelegant to use power tools where hand tools will suffice. These are definitely power tools. They're extremely useful. They let you do things you wouldn't be able to do otherwise, but they can also get you into trouble that you haven't thought of before. So, wanted to thank Novozymes, which is where I got the first two case studies, and Adjust where I got the last one. And now I'm open to questions.
I've got a few. Okay. Actually, so while creating an index as being a DBA, should I really focus on the default fill factor or the fill factor?
So that's a different advanced question. I would say 90% of the time you don't need to, but there are those cases where your specific write pattern needs it. So I would say it's helpful to think about whether you're going to end up with lots of like B-tree page splits. And basically that's where you think about the fill factor. In most cases, it's probably not so important, but in some cases it may be.
My another question would be, is there any way to reduce the size of the B tree? Because sometimes the size of my table is like 5 gigabytes, and the B tree index itself is like 1.5 gigabytes. I don't really want to use Brin because my database table has lots of updates and deletes as well. So is there any mechanism to reduce the size of B tree?
So some of the newer versions of Postgres have some kind of neat tricks in that regard. Otherwise, if you're indexing data because you're only, say, checking some part of it, you might be able to prune down that in some way or another, and the expressional indexes might help you. But it's really difficult to know without a complete use case. For B trees, it sounds like you probably have like a really narrow table and an index on a bunch of very distinct values, in which case there might not be a lot you can do.
My last question would be, it's not about index, but it's more about the table itself. So, sometimes the tables have so many updates and deletes. Auto vacuuming helps sometimes, but sometimes there are like lots and lots of date tuples. I really want to do the vacuum full on the table itself. So should I really stop myself, or should I go ahead? Because the date tuples are like in the numbers of millions. So what would you recommend?
Vacuum full is usually, but not always, the incorrect solution. I would say vacuum full is another power tool. I've worked on databases where we had to like disable auto vacuum on certain tables and just vacuum full them all the time. But those were cases where we had a very small number of active tuples and a very, very large number of dead tuples. So in the case where like 5 or 10% of your table is actually live and the rest is dead, vacuum full is often something that will perform better. The downside is the locking stuff, and you have to balance those two out. So that's kind of where I would have personally found the line in that area to be covered.
So for tables where people, you already know that there are going to be large amounts of updates and deletes, perhaps there are auto vacuum settings that can be tuned a little bit to.
So yeah, I mean, obviously, if you can make auto vacuum more aggressive, that's your first topic. That's your first approach. Usually I say the more aggressive you make auto vacuum, the better. So my first step personally is usually to disable all the auto vacuum cost delay stuff. But I know some people prefer, or some people worry about things like flushing stuff out of disk caches in those cases. But like in very specific cases where maybe you have a small table and that table is consistently being updated over and over again, or maybe you're writing to that table and then deleting everything out of it and then writing to it again and deleting everything out of it, in those specific cases, you're going to have to make some decisions.
Thank you. I have not particularly for index, but something that we had in our database. There was duplicate record for certain sets of rows. duplicate with the primary key also being duplicated. And in some queries, the duplicate record were not returned, but in some queries it was being returned. So how do you explain that?
Corrupted indexes. Now, if these are indexing text fields or something like that, there is a most likely cause of that corruption.
It was created because there was a text error in our database, and during that time, any records that was created was created in order to duplicate that.
Okay.
So later, what I did to solve was I found the CTID.
Yep, that's exactly what you do. Yeah, find the CTID. One thing that can really cause this duplicate record problem is if you have indexes on text fields and they need to be unique. And if you were using Ubuntu about like 4 years ago, I think, 3 or 4 years ago, I don't remember the exact time, but they backported a glibc massive set of collation changes without updating the glibc version in a major stable version of Ubuntu. Or if you just upgraded glibc across that problem, you'd have a similar issue, because with the collation changes, remember, indexes are collation order dependent. You're doing an order-based search. If that ordering is different at runtime than it is on disk, you may not find the record when you go to check uniqueness. And now you're going to have two index entries in the unique index, but they're going to be in different spots. So the tool to use to check that is amcheck, and amcheck should tell you if you have some of those problems.
So, Chris, you said that we should not use power tools when we have the hand tools.
Yes.
I totally agree. But we sometimes have to use the power tools.
Absolutely,
right?
absolutely.
So from your experience, how does that play in regards to when upgrading a database server, the backward compatibility? So what has your experience been so far?
These things very rarely impact upgradability.
Okay.
There are, but you will sometimes run into them and then they are unexpected.
Right.
So for example, I was helping somebody with a major version upgrade not too long ago, and ran PG upgrade, and it's like, you have custom aggregates using any array. You can't do that. We use PG upgrade. And went through, found that we weren't actually using those aggregates anyway, and just dropped them and went along with it. But usually it's not a problem. The thing is that there are very specific corner cases where it can be, and then you've got to then figure out what you're going to do about it.
So has it mainly been functional incompatibility or index types are the major hurdle when upgrading?
So if like index types, you're talking about extensions. Obviously, you have to have the extension ready on the new version as well as the old version, but that's the only issue there. I would say index types themselves are like the least of the concerns.
Thank you.
In OLTP environment, I have one table huge number of records, right? So with many insert update deletes, then the index will be scattered. Yeah. What would be your recommendation? How frequently I have to rebuild the indexes in PostgreSQL?
So, so explaining the specific problem here. The issue that you're likely to find is that many of these leaf nodes may point at dead tuples, and then auto-vacuum will then reclaim the space, but when it compacts the pages, some of these pages may not be fully used and stuff like that, right? I find that auto-vacuum actually does a pretty good job usually of maintaining the index size. It's very different from the table. The table, auto-vacuum can only clear blocks at the end of the table, and then only if it can get an exclusive access block really quickly when it's ready to do that. So I would say the index fragmentation issue, just from inserts, updates, deletes, is probably not going to be the issue that's going to cause you to have to rebuild things. It's more likely going to be a case like in this one particular case, when I worked at Adjust, we had tables where we would load a lot of data, then we would delete that data and insert it somewhere else into a new table. And we would do this over and over and over again, like every 20 minutes. And consequently, you could end up with a table with 12,000 live rows and 30 million dead rows. And in those particular cases, auto vacuum will just simply never keep up. And so in that particular case, you just have to run vacuum full, right? But typically, if you're going to be in those cases, you're going to be behind because auto vacuum is slow and not, rather than because the index is getting fragmented. In other words, auto vacuum will handle most of that for you, but it doesn't help you out if it's slow. Go ahead.
I have a question about big tables. Suppose I have an index like on a terabyte, 1 terabyte, and then index size is 25 or 30 gigabyte. It works fine. I have a query, I will show that it works fine until it's 1 terabyte. But when there is a like data is growing day by day, and it turns out index size doubled in over a year, going to the 2 terabyte, 3 terabyte, index size is like 50 to 60. Same query is slowing down the performance. What would be a next step? Like how would you tackle in order to maintain a same query speed that was before on a smaller index size and got degraded? Like does that even matter that if index size grows way beyond like a 60 gigabyte, 80 gigabyte?
So there are several things which can make it slower. The first is that if it's much faster if the index is in memory than if it's on disk and you have to look at it. Remember that querying an index is going to have a logarithmic complexity, right? So if you double the size of the in this particular case with four branchiness of 4, if you quadruple the size of the index, you're really only adding probably one more layer of query, right? So usually the size of the index by itself isn't necessarily the problem. The problem may be if it's not all fitting in memory, or if a large number of the nodes that you're looking at may already be dead, then scanning the index is going to be slow just because it's hitting a bunch of rows that are not visible and it has to check them. In Postgres, the indexes do not store visibility information. So one thing I did see also at the Novozymes project was we had a table where we kept, basically it was a big queue. So you'd write on one side and you'd be deleting one row at a time off the other, right? And if you had a long-running transaction, then auto vacuum couldn't clear those rows, right? And so what would happen is you have maybe 20 million dead rows at the head of the index. And you're saying, give me the next row, and it's checking 20 million rows for visibility. And that caused some fun, not only performance problems, but some other bugs because we were using those with advisory logs. We didn't have the transactional ones. So there were some timing issues there also. But like if you're talking about indexes being slow, those would be the two things I'd think about. One is not fitting in memory, and the second one is checking a whole bunch of tuples for visibility. And then I guess the third one is maybe using the wrong index. So good reason to check the query plans. All right. Well, thanks everyone. And if you have any more questions, I'm happy to take them outside.
Okay, thank you.